At 7:37 in the morning on June 8, 2026, a Monday, the ground beneath the Sarangani province of southern Mindanao lurched sideways and downward simultaneously, and the Philippine Institute of Volcanology and Seismology's instruments registered what would become one of the most significant seismic events in Philippine history in the modern monitoring era. The initial automated estimate said magnitude 7.0. Within hours, after seismologists at PHIVOLCS, the USGS, and the European Mediterranean Seismological Center finished their analysis, the number was revised upward to magnitude 7.8, the sixth largest earthquake ever, recorded in the Philippines. The epicenter sat 32 kilometers west of Masim, Sarangani, at a depth of approximately 33 to 57 kilometers, depending on the agency's methodology, and the mechanism confirmed what geologists had been predicting for years about where the next major energy release in the system would come from. By 11 in the morning, PHIVOLCS had already cataloged 138 aftershocks, ranging from magnitude 1.3 to a magnitude 6.7 that hit less than 3 hours after the main shock. Tsunami waves reached the coasts of Kiamba and Masim at approximately 1 meter in height. The highest intensity reported was PI's 7, classified as destructive, felt in General Santos City. The shaking traveled as far as Leyte, hundreds of kilometers to the north. And sitting underneath all of that verified operational data is a geological story that the Philippines has been building toward for decades, a story about one of the most complex and dangerous fault systems on Earth that scientists have been warning would eventually express itself exactly this way. And the June 8th event confirmed the specific prediction that many researchers had placed at the top of their concern list. To understand what was confirmed on June 8th, you need to understand where the Philippines sits in the global tectonic architecture, because the country does not sit on a single dangerous fault. It sits at the intersection of multiple dangerous fault systems operating simultaneously, and each of them carries its own category of threat. The Philippine archipelago is the surface expression of one of the most geologically active convergence zones on the planet. The Philippine sea plate is moving toward the Asian continental margin at approximately 70 to 100 millimeters per year, depending on the location along the boundary. That convergence does not happen cleanly along a single line. It is accommodated by a system of trenches, subduction zones, and strike-slip faults that divide the convergence motion among multiple structures, each of which accumulates stress independently and releases it on its own schedule. The result is a country where major earthquakes are not unusual events that punctuate long, quiet periods. They are regular features of the geological environment, built into the physical structure of the islands themselves. The specific structure that generated the June 8th event is the Cotabato Trench, which runs along the southwestern coast of Mindanao, where oceanic crust of the Sunda Plate beneath the Celebes Sea subducts beneath the Philippines' mobile belt. PHIVOLCS's primer on the June 8th event stated directly, based on the location of the earthquake, focal mechanism, and aftershock distribution, the earthquake may be attributed to subduction along the Cotabato Trench. The attribution matters, because the Cotabato Trench has a documented history of catastrophic events that the geological community had been citing as the basis for their concern about this zone for years before June 8th arrived. The most relevant precedent in that history is 1976, when a magnitude 8.0 earthquake and tsunami along the same trench killed 8,000 people in what remains the deadliest natural disaster in Philippine recorded history. The 1976 event struck at night when fishing communities along the Moro Gulf were on or near the water, and the tsunami that followed the main shock arrived within minutes with essentially no warning infrastructure in place. The death toll was driven primarily not by the shaking itself, but by the water. The June 8, 2026 earthquake struck the same trench system, confirming seismologists' prediction that this zone retained sufficient accumulated stress for another major event, despite the 1976 release. The aftershock sequence exceeded 258 events in the period immediately following the main shock, underscoring the scale and persistence of the ongoing seismic adjustment. What that aftershock count tells you in scientific terms is that the June 8th rupture, while significant, did not release all of the accumulated stress along the trench. The aftershocks are the sound of the system redistributing the stress that the main shock left behind, adjusting and settling into a new configuration, and that redistribution process produces its own events because no large rupture leaves the surrounding crust in a stable state immediately afterward. The focal mechanism of the June 8th event is the detail that specifically confirms the prediction, and it requires a moment to explain why mechanism matters as much as magnitude. A magnitude number tells you how much energy was released. A focal mechanism tells you how the fault moved, whether it was a thrust, a strike slip, or a normal fault, and in which direction. The Cotabato Trench is a subduction zone, which means the dominant mechanism should be thrust faulting, where one plate is forced under another and the upper plate lurches upward and seaward. That is exactly the mechanism PHIVOLCS identified for the June 8th event, and it is also the mechanism most efficient at displacing the water column above the fault to generate tsunamis. The combination of thrust mechanism plus shallow to intermediate depth plus offshore location is the specific set of conditions that tsunami scientists had identified as the worst-case scenario for Mindanao's western and southern coastlines, and June 8th produced exactly that combination. Tsunami waves were recorded along the coasts of Kiamba and Masim, Sarangani, and Kalamansig, Sultan Kudarat, with a height of approximately 1 meter, based on data from PHIVOLCS sea level monitoring stations. Waves less than 1 meter were also recorded in Madi City and Zamboanga City. 1 meter sounds modest relative to the historic images of the 2004 Indian Ocean tsunami or the 2011 Tohoku wave, but 1 meter of tsunami water moving at the speed a wave travels when it is driven by a magnitude 7.8 rupture carries enormous destructive force, and the communities along the southern Mindanao coastline are not sitting on the elevated terrain that would buffer them from even that wave height. Fishing communities, low-elevation shoreline settlements, and coastal commerce areas directly in the tsunami's path had minutes between the earthquake and the first wave arrival. PHIVOLCS issued its tsunami warning and evacuation. Protocols were activated. The death toll from the tsunami component of this event was limited specifically because those systems functioned. That is worth stating directly because it is the contrast with 1976 that validates the investment in warning infrastructure that the Philippines has made over the intervening 50 years. But the June 8th event is not the whole story of why scientists say their worst prediction was confirmed. It is the most recent chapter in a longer pattern that the geological community had been documenting for years before June 8th arrived. The Philippine Fault System, which is the structure most people are referring to when they talk about earthquake risk in the northern and central Philippines, is a separate system from the Cotabato Trench. It runs for approximately 1,200 kilometers along the length of the archipelago in a northwest-southeast orientation, passing through some of the most densely populated regions of the country, including parts of Luzon, the Visayas, and Mindanao. The Philippine Fault is a left lateral strike-slip fault, meaning the two sides of it move horizontally past each other rather than one being thrust under the other. Strike-slip faults do not typically generate the tsunami-producing vertical displacement of subduction zones, but they are extraordinarily efficient at producing intense near-field shaking. Over long distances, and the Philippine Fault runs close enough to major population centers that a large rupture on it would directly shake cities, rather than producing its damage primarily through secondary water effects. The documented historical behavior of the Philippine Fault includes multiple magnitude 7 or greater events over the past century, including a magnitude 7.8 in 1990 that killed more than 1,600 people in Luzon and caused damage across a corridor hundreds of kilometers long. That 1990 event demonstrated what the Philippine Fault can produce when it ruptures across a significant length of its trace. The scientific concern that had been building in the years before June 8, 2026 was not about the Cotabato Trench alone. It was about the overall state of loading across the entire Philippine tectonic system, which includes the subduction zones at both the eastern and western margins of the archipelago, the Philippine Fault running down the center, and the Cotabato Fault System in Mindanao. The 2026 event is only among several major Philippine earthquakes that occurred within the same general area over the past century. Mindanao lies across the convergent boundary between the Sunda Plate and the Philippine Sea Plate. The strike-slip component of the convergence is accommodated partly by the Philippine Fault System and partly by the Cotabato Fault System, a network of NWSE trending sinistral strike-slip faults. That statement from the geological record is the key to understanding why June 8th confirmed rather than merely demonstrated something. The convergence between the Sunda Plate and the Philippine Sea Plate does not have a choice about where it goes. The physics of plate tectonics requires that the motion between converging plates be accommodated somewhere, and if the subduction zones are locked, the motion backs up into the strike-slip systems. If the strike-slip systems are locked, it backs up into the subduction zones. The system as a whole is accumulating motion that has to go somewhere, and the June 8th event confirmed that the Cotabato Trench is not yet finished, releasing the stress that half a century of convergence since 1976 has loaded into it. A magnitude 7.8 is a large earthquake, but the 1976 event was magnitude 8.0, releasing approximately twice as much energy, and it ruptured a significant length of the trench. For the same zone to produce a 7.8 in 2026 after only 50 years of reloading suggests that either the 1976 event did not fully relax the entire trench, or the loading rate is fast enough that significant stress had rebuilt in only half a century, or both. Seismologists had been warning about all three of those possibilities in the years leading up to June 8th. The event confirmed that, at minimum, the second and probably both are true. The human geography of southern Mindanao amplifies every one of these geological realities. The highest reported intensity was PEIS 7, classified as destructive, which was felt in General Santos City. General Santos City, often called Jinsan, is a major port and commercial center with a population of approximately 600,000 people. It is located directly in the zone most exposed to both the strong shaking from a Cotabato Trench event and the tsunami waves that such an event generates. The city sits on coastal terrain that offers limited elevation for rapid tsunami evacuation. The same fishing economy that makes the region economically active also places large numbers of people at or near sea level during the hours when earthquakes can strike without any warning. The June 8th event struck at 7:37 in the morning, when fishing activity would already have begun and when coastal communities would have been active in ways that put people near the water. The fact that the tsunami waves recorded at 1 meter did not produce a large number of fatalities from water inundation reflects both the relatively modest wave heights at this specific event and the functioning of the evacuation system, not an inherent safety of the coastline geography. What scientists are watching most closely in the aftermath of June 8th is the behavior of the surrounding fault systems, because large earthquakes do not leave their neighboring structures unchanged. The mechanism of Coulomb stress transfer, which describes how the energy released in one earthquake redistributes stress to surrounding fault segments, is well established in seismological literature and consistently observed in the aftermath of large events. The 1976 magnitude 8.0 loaded specific segments of the surrounding fault network. 50 years of subsequent convergence loaded them further. The June 8th magnitude 7.8 released stress from the rupture zone but loaded the segments adjacent to it, specifically the sections of the Cotabato Trench, to the north and south of the June 8th rupture, the Cotabato Fault System that accommodates the strike-slip component of the same convergence, and potentially segments of the Philippine Fault in Mindanao that carry some of the same regional convergence. The aftershock sequence that produced 258 events in the immediate aftermath is part of that redistribution process, and monitoring agencies will be watching for any migration of aftershock activity in the weeks and months ahead that might suggest stress is building toward a secondary rupture on an adjacent structure. The specific concern that motivated the worst prediction language from scientists before June 8th was about cascading rupture sequences, the possibility that a large event on the Cotabato Trench could promote failure on the Cotabato Fault System or on segments of the Philippine Fault in sufficient proximity to be affected by stress transfer. The historical record of the region includes examples of earthquakes occurring in sequences where one major event is followed by another on a different but nearby structure within months or years, and the June 8th event puts the regional stress field in the configuration that scientists had identified as most likely to promote exactly that kind of cascading behavior. Whether it actually occurs depends on whether the ambient stress in the neighboring structures was already close enough to failure that the transferred stress from June 8th is sufficient to push them over the threshold. That is a question the monitoring network will be answering in real time over the coming months. The infrastructure exposure in this region is not limited to the immediate Sarangani and General Santos area. The southern Mindanao corridor is a major agricultural and fishery production zone whose supply chains feed markets across the Philippines and Southeast Asia. The port infrastructure at General Santos handles tuna landings that supply processing facilities serving global markets. The road networks connecting the region to the rest of Mindanao cross terrain that is vulnerable to landslides triggered by seismic shaking, and the June 8th event produced ground acceleration values sufficient to destabilize slopes across a wide area. The underwater communication cables that carry internet and telecommunications traffic between the Philippines and the broader regional network cross the seabed in the vicinity of the Cotabato Trench, and ruptures at that zone have historically produced seafloor disturbances capable of severing those cables. The PHIVOLCS tsunami warning covering coastal areas of Mindanao and the Sulu archipelago following the June 8th event cited the possibility of waves exceeding 1 meter in exposed coastal zones, and evacuation protocols across Mindanao coastal communities were immediately activated following the warning issuance. That immediate activation of evacuation protocols is itself a confirmation of a different kind of prediction. The prediction that investment in warning systems and community preparedness translates into reduced mortality when events occur. The contrast between the 8,000 deaths in 1976 and the significantly lower toll in June 2026, despite a comparable magnitude, is not accidental. It reflects decades of work by PHIVOLCS, the local government units along the affected coastlines, and the international community that supported the development of the Pacific Tsunami Warning Center and the regional network of sea level monitoring stations that gave decision makers the measurements they needed to issue accurate warnings within minutes of the main shock. But the confirmation of preparedness infrastructure working does not change the underlying geological reality that June 8th brought into sharp focus. The Philippines sits on the Pacific Ring of Fire and experiences regular earthquakes from multiple fault systems throughout the archipelago. In 2026, the Philippines has recorded 169 earthquakes of magnitude 2.5 or greater so far. That number represents the background seismicity against which the June 8th event stands out, not as an anomaly, but as a punctuation mark in an ongoing geological sentence. The Philippine tectonic system is not resting between events. It is continuously loading, continuously adjusting, and continuously generating seismicity across a network of structures that scientists have been mapping and monitoring with increasing precision for decades. The worst prediction that scientists made was not about a specific date or a specific magnitude. It was about a specific configuration. They predicted that the Cotabato Trench retained sufficient stored stress for another major event capable of generating a regionally significant tsunami, affecting the densely populated coastlines of southern Mindanao within a geological time frame that made it relevant to current infrastructure and population planning. June 8th confirmed that prediction. The trench ruptured at the magnitude and mechanism that scientists had identified as the most likely and most consequential scenario for the region. The tsunami it generated, while smaller than the worst-case modeling had suggested for a full-length trench rupture, was real and measurable, and arrived at populated coastlines within the time frame that had been used to calibrate evacuation protocols. The aftershock sequence it produced was larger than median expectations would predict, with a magnitude 6.7 occurring within 3 hours of the main shock, which itself would be a significant earthquake in most contexts, but was reduced to an aftershock by what preceded it. What comes next in the scientific analysis of this event will determine how much the June 8th rupture has changed the stress field in the surrounding fault network, and therefore how the probability assessment for future events on nearby structures should be updated. PHIVOLCS and its international partners will be conducting detailed aftershock relocations to precisely map the geometry of the ruptured fault segment. They will be comparing the GPS measurements from stations across Mindanao before and after the event to determine how much the ground moved and in which direction, which allows them to calculate the slip distribution on the fault plane and identify which portions of the trench moved the most and which moved less or not at all. The segments that moved least in the June 8th rupture are the ones that remain most highly stressed afterward, and those are the segments that will carry the highest probability of generating future events. The Philippine tectonic system will continue doing what it has been doing for millions of years, regardless of what any monitoring agency observes or any government plans for. The Sunda Plate will continue moving toward the Philippines. The Philippine Sea Plate will continue its convergence with the Asian margin. The Philippine Fault will continue accumulating the stress that the oblique component of that convergence puts into it. And the Cotabato Trench, which just confirmed that it is still an active and capable source of major earthquakes and tsunamis, will continue loading its remaining unruptured segments with the energy that June 8th transferred to them. The question for the Philippines, as an institution, as a government, as 115 million people living on one of the most seismically active archipelagos on Earth, is whether the infrastructure, warning systems, evacuation plans, and building standards that will determine who survives. The next confirmation of the worst prediction will be in place when it arrives. June 8th demonstrated that the warnings work when activated. The geological record demonstrates that there will be another event to activate them for.